In the last videos, we talked about the QR decomposition using householder transformation. If you have a matrix A and you want to decompose it into a product of an orthogonal and an upper triangular matrix, then this is not a unique decomposition. There are several Q's and several R's to decompose the matrix. So, and now there was a man named Givens. He also lived, I don't know, 200 years ago. And he had also an idea, a different idea as householder had, but also an idea about how can we decompose into a product of two matrices. If you remember how we proceeded analyzing householder, then we analyzed a lot before we started, and then I gave you some examples with numbers. In this video, I will start with examples, and the theory is not that big, so we will do that on the fly. We will do that in the end of the video. If we have a matrix A in there, we have two entries S and T. Then here I tell you how to build a Q matrix, and then we multiply Q times A, and then we get a 0, the desired 0 at that position. But let's give you an example with numbers. Let's say the matrix is the matrix, and now we want to kill that 4. It's the same as we did doing Gaussian elimination. We want to kill that 4, and we will use that 3 to kill that 4. And how do we do? Now we are creating a Q matrix, which is orthogonal, and we will follow some simple steps. Let's name that matrix Q to 1, okay, to kill the second element. And here we do the following. We have to consider the 3 entry and the 4 entry, and the 3 entry, let's name it S, and the 4 entry, let's name it T. That's what we did in the script. And then we build the matrix S3 divided by square root of 3 squared plus 4 squared, 9 plus 16, 25, and the square root of that is 5. So that was my example to get here a number and not square root 26 or 27 or ugly things like that. So in this case we get a 5, and then in this position to 2 the same entry again. Then here in that position we use the 4, this 4 divided by 5, and here we use a minus 4 divided by 5. Okay, these two entries are interesting. Here the 3, here the 3. The denominator is the square root of these two squared. And then here we use that element, and here we use that element, but with a minus. And apart from that, we use 0, 0, 0, 1. If this matrix was larger than ones on the diagonal, apart from that block here in the first column and second column, first row and second row. And now let's multiply with A, and what do we get? Here this entry is that times that, so 9 divided by 5 plus 16 divided by 5, it's 25 divided by 5, which is 5. This entry 0 times plus 5 times 4 divided by 5, which is 4. And here 3 divided by 5 plus 4 divided by 5 plus 0, it's 7 divided by 5, 1.4. And now the interesting entry, minus 12 divided by 5 plus 12 divided by 5 plus 0. This is the desired 0, and that was the reason why we built that matrix. We wanted to get a 0, and using the numbers we did here, this 0 is guaranteed. Okay, and now let's calculate all the other entries. Then we get a 3 minus 1 divided by 5, and this is a copy of that line. So this is the transformed matrix, and we have a 0. Now we want to kill the 1. So we consider these two entries. We need the square root of 5 squared plus 1 squared. This is square root 26, and we don't like these numbers. So let's change the example for the sake of simpler numbers. It's very hard or near to impossible to choose numbers so that all steps keep simple. So my idea was, okay, let's change the matrix. For understanding being a student, let's assume that was the result here. And so now we can continue with numbers and the calculations are not that ugly. That's the matrix 3, 1, and we want to kill in A. And how do we build? Okay, we have a first column and a third column. We have a first line and we have a third line, and apart from that, let's use the structure of the identity matrix. That is the structure of the identity matrix. Now again, this is 3 and 4 as it was before, so these numbers also will be 3 divided by 5 and so on. So to make clear, these are the special numbers and these were the special numbers here. And after these numbers, these entries will come to life. Let's multiply with A. So here 9 divided by 5, 16 divided by 5, which is 5. 6 divided by 5 plus 8 is 14 divided by 5. 3, 24 is 27. Second line is kept. And the third line, now the interesting entry, minus 12 plus 12 and a 0 in between. So we get the desired 0. Minus 8, 0, 6 divided by 5. So it's minus 2 divided by 5. And minus 4 divided by 5 plus 18. So it's 14 divided by 5. Okay, now what's the next step? We want to kill this entry by using the 6. Now S is 6, and then we build these numbers. But for the sake of simplicity, we want to avoid the minus 0.4. Let's assume the matrix is. This time square these entries, add them and take the square root. It's not a natural number, but we have a square root of 5. We have the second and the third line here, and so we take the structure, take identity matrix, and the second and third column, second and third row, there we put in these numbers, and apart from that, let's use the structure of the identity matrix. So that's the structure of the identity matrix, and that's the 4 positions, second and third line, second and third column. What are the entries? This time square root 5, 1 divided by square root 5. Then this entry again here, and then 2 divided by square root 5 and minus 2 divided by square root 5. Let's multiply. And we get the first line is copied, and then the second line. 1 divided by square root 5 plus 4 divided by square root 5. So we have 5 divided by square root 5, which is square root 5. Here we have a 0, and here we get 5/12 divided by square root 5, and the sum is 17 divided by square root 5. Then here we get a 0, and here we get minus 2 plus 2, we get the desired 0, and here we get minus 10 plus 6, which is minus 4 divided by square root 5. So this is how it works for 3 by 3 matrices. Now the questions you may have is, what is if the matrix A is larger? So let's also have an example for that. We follow the structure. Here we have a 0, 0, 0, 0, 0, 0. This is the first position. We don't have a 0, so we start killing here at that position. We want to kill in the 5th line, second column, using this entry. So it's 2, 5. So we have Q, 5, 2. And what do? We have 1 column, 2 columns, 3, 4 and 5, and we have 1 line, 2 lines, 3 lines, 4 lines and 5 lines. Now position 2 and 5. So 2 and 5, 2 and 5. So these are the positions for our entries. In these lines, apart from these entries, we have zeros. And apart from that, we use the structure of the identity matrix, which is 1 on the diagonal and zeros outside the diagonal. And what are these entries? We have 3 and 4, and so it's the same as we had. We use the square root of 3 squared plus 4 squared, what is 25, and the square root of that is 5. So this entry divided by that length, so it's 3 divided by 5, and 3 divided by 5 here also. And here we have 4 divided by 5 and minus 4 divided by 5. If we had a minus 4 here, then here we would have a minus, and here we would have a plus. Okay, that's the Q matrix. And now you can multiply Q52 times A. And if you do so, what is the structure? The first, the third, and the fourth line is a copy. And the second and the fifth line is not a copy. Here we get the desired 0, but unfortunately, due to the fact that we have a 7 here, we get an entry here. So we kill an element, get a 0, but here at that position, we introduce an entry, but we always follow that structure. First kill here, first kill here, kill here, kill here. Please feel free to redo the calculations by your own. Okay, let's go back to the script here, but a little more in general. Okay, and in the end, what do we have? We multiplied Q21 times A, and then we got this 0. Then we took the result, multiplied by that matrix, then we got that 0, and then we multiplied by that matrix, and then we got that 0. So in the end, in total, we multiplied A times this matrix, right, middle, left. And then we have the following, let's say Q3. I skipped that index so that we have to write not so much. But what do we want? We want a QR decomposition, so we have to bring these matrices to the right hand side. Doing householder, we had the same element here talking about. Now let's multiply with Q3 transposed from the left. Then we have Q3 transposed times Q3. What is identity? So we can kill, and on the right hand side we get Q3 times R. Always be very careful what factor is on the left and what is on the right, because A times B is not the same as B times A, so we have to be careful. Then bring the Q2 to the right hand side and then multiply the equation from the left with Q2 transposed, and then we get Q2 transposed, and then bring Q1 to the right hand side. Multiply from the left with Q1 transposed, and you get, and so this product is our Q matrix. And now we have our decomposition. Here in the script I have an example, and I did not care about the odd numbers, and so this is the example. First consider -1 and 2, square them, 1 plus 4, take the square root 5, then take -1 divided by square root 5, -1 divided by square root 5, and here 2 divided by square root 5, and -2 divided by square root 5, and apart from that, use identity matrix structure. Then, if you apply that, Q1 to the left and A to the right, if you redo all the calculations, here you get the desired 0. This line is kept, and the other entries are the entries I wrote down here, and you can try to recalculate them. Now we want to kill that 2 using the 2.2361. So this time as this S is that number, this T is that number, square S, square T, add them and take the square root of, and you get some number. And then take 2.2361 divided by that number, and then you get 0.7454. Reuse the number here again. Here you have 2 divided by that number, and here we have minus 2 divided by that number. And apart from that block, because it's position 3 and 1, use identity matrix structure and entries, and so we have this matrix. And then apply that matrix, multiply Q2 times that matrix, that is Q1 times A, the transformed A, and then doing so you get this matrix. Here the desired 0 is kept, and this 0 is the new 0, the one we wanted to produce. In this case, the second line is kept, you see here. Now we want to kill that entry, and we want to use that number, so minus 0.8944 is the S, 2.5342 is the T, square them, add them, take the square root, that's the denominator, and then minus 0.8944 divided by that number, this is that entry, reuse the entry here again, and then 2.5342 divided by is 0.94, and take the negative of that. And apart from line 2, line 3, use identity matrix, so these entries and this one, and then multiply Q3 times that matrix, and then you will get that. These zeros are kept, and this is a new 0. And now we have the upper triangular structure, and now we have our decomposition, or we have the R part of the decomposition. Now we have to multiply Q1 transpose times Q2 transpose times Q3 transpose, and that is our Q matrix. And now we decomposed A. A is the product of this Q and this R. And if you do these calculations, you will get that matrix. That's not so much fun, but using electronic help, maybe you can also reproduce these entries, and here the R is a copy of that. Okay, I hope you understood everything well. Now some annotations. Look at the columns of A, or the transformed columns of A. I will show you. Okay, let's take this column, and let's say this is a vector, -1, 2, 2. What is the length of that vector? The length is -1 squared plus 2 squared plus 2 squared, which is 9, and the square root of that is 3. So the length of that column is 3. And let's test the length of that vector, and this length will also be 3. Please feel free to check that, and the length of that vector is also 3. And this is true for the first column, but also for the second column. This length is square root 29. If you calculate that length, it will also be square root of 29. The length of that vector is also square root 29. And the length of that is also square root 29. And the third column, this is length square root 3. The length of that is also square root 3. The length of that is also square root 3. And the length of that is also square root 3. So the length of each column is kept in the proceeding doing the QR decomposition using givens. But it's not a speciality of givens. That is always true if the matrices here and here are orthogonal. Then it will always be true. Then the length of the columns is kept through the whole process. So also doing householder, this is also true. You can check that for the examples we had in the last videos, and there it's also true. And so in some sense, I don't want to go too much into detail, then a mathematician would say this is a stable algorithm because the length is kept. The length is not kept if you do the LU decomposition, but for the QR transformations, this is stable. The length is always kept. Okay, we want to program that. Then what can happen if one element S or T is 0? That doesn't matter, then not so much will happen. If S is 0, then the rows will be swapped automatically by that process. And if the T is 0, then the matrix we introduce is identity matrix and nothing happens. But what if two zeros are there? So if A is, for example, 0, 0, 3, if this is the matrix, then this S is 0 and the T is 0, and that's what we have to take care of in the algorithm. Otherwise, we will get a division by 0. That's what I say here. Okay, if you compare the time which is consumed doing these operations, then the number of operations is more or less double the ones compared with LU decomposition, so it will take double the time. And that means that, being maybe the maker of MATLAB, you will say, okay, this QR decomposition will take double the time, so maybe it's not that interesting, but it's not more than double the time, fortunately. Maybe if you have a look in other textbooks, so in my script we have Q1 transposed, Q2 transposed, and Q3 transposed, and in other textbooks you will get that, and then maybe you wonder, but that's not so hard, because you know the rule AB product transposed is the same as B transposed times A transposed, and because that is true, then A times B times C transposed, it's also true that C transposed times B transposed times A transposed, and so these two are equivalent due to that fact. Okay, and now we can do the implementation. Let's call givens decompose, and then having the decomposition, we can multiply the right hand side by Q transposed, and this is the right hand side for the back substitution process with the matrix R. That's exactly the same as we had last time. Now here the implementation of the decomposition. Let's find out what is the size of matrix A, and then let's start with the Q matrix being the element changing nothing when multiplying, so we don't need an if else here. Okay, let's start doing the elimination process. Let's work in the first column. Let's kill in the second to the last row, and then go to the second column and then eliminate in the third till the last row, and so on. So this is this nested loop. Let's have the Q matrix, which is more or less identity. Then let's calculate the elements here, square root for the denominator, and then we can fix in this block. This is very comfortable MATLAB, and be careful, this letter is not a 1, it's an L. Yeah, this L, so it's very dangerous using the variable L. It looks like the 1, but here if you compare the L and the 1, you see, okay, there's a very, very small difference, so be aware of that. So this is L, this is L, L, and a L, and a L, and an L. And then here we have our entries, and then we transform A, starting with A, that's what we have here, and then transform it from one step to the next, and you will get a lot of zeros. Due to rounding errors, they will be not exactly 0, because we know from the theory it must be a 0. Let's use trio, that's triangular upper. So in the end, out of a matrix, we will take only that part. The trio command introduces 0 below the diagonal. And then let's collect the Q's, and it's very important if you write Q is qt transposed times q, or if you write q is q times qt transposed. And when I programmed that script, I've chosen the wrong one, and then I found out that this was wrong and this is the correct one. Why? The new factors are on the right hand side, and that's what we can see here. The new q's are on the right hand side. So the new q is on the right hand side. So this is givens. And in the end, I want to give a little theory on my paper. So if we have, for the sake of simplicity, a 2 by 2 matrix with these entries, then we build our Q matrix by squaring the entries and adding that and taking the square root. We can also write it that way. And then we use S, T, and minus T. And when we multiply Q times A, then we have, and what do we get? We get S squared plus T squared, and we get minus ST plus ST, which is 0. So the 0 is guaranteed using that structure. And then we have AS plus BT, and we have minus AT plus BS. And what do we see? We see this 0, and on top of that we can study the length of that column. The length of that column is S squared plus T squared divided by square root S squared plus T squared, which is square root S squared plus T squared. So the length of that is exactly the length it was here. Then the second column, the length is AS plus BT squared plus minus AT plus BS squared. And let's don't forget the denominator. This is this one squared, so S squared plus T squared. And what do we want to see? That this number is equal to square root of A squared plus B squared. But we don't see in the first moment, so you have to expand these parentheses. And then we have A squared S squared plus B squared T squared plus 2ABST. And then from here plus A squared T squared plus B squared S squared minus 2ABST divided by S squared plus T squared. And then we have plus minus, and now we can factor out an A squared, and we have an S squared from here and an T squared from here, and we can factor out a B squared, and then we have T squared plus from here and an S squared from here divided by S squared plus T squared. And now this cancels, and we have A squared plus B squared. And the length of that was not what I've written down, but the square root of that. So square root of that, square root of that, square root of that, square root of that. And that means that we have proved the length here is kept. Okay, that's it. Now we have talked about the QR decomposition using givens transformations or givens rotations. Where does the name rotation comes from? The matrices we used are also rotation matrices. I don't want to talk too much about, but if you want to rotate in the XY plane, then you have to use matrices with the structure we had, and so you can also view that as a rotation. Okay, that's why we sometimes say transformations and sometimes we say rotations.